In this lesson, we'll be talking about moving boundary work. So we're still dealing in a closed system. So state 1, we have a piston cylinder here. We've had it compressed. It is compressed down to a shaft length of x. The area of the piston head is area A. And below it, we've denoted a graph of pressure versus volume. So the volume is it's constricted now, it's compressed, so the volume is very low. The pressure is pretty high though at state 1 because we've compressed it, so we've increased the pressure. So then if we were to expand this piston head, we would see it would expand down, the volume would increase, the pressure would decrease. We'd have this process occurring going from pressure state 1 to state 2. We don't know the exact process that how it would go, so we leave it as a dotted line. We don't know the exact characteristic of the process, exactly if it's a straight line, if it's exponential, if it's going to be logarithmic. If we don't know how it gets there, the path of the process, we leave it as a dotted line. And we've increased our volume by, the area hasn't changed, but the shaft length of the tube has changed. So that change is going to be dx, the differential of x, that change of x. So we've created some work now, right? So we've had del of this moving boundary work. That's what we call whenever we move a boundary, this moving boundary work. Now that's going to equal to, all work is basically equal to a force over a distance. So the distance it's traveled is dx. And we can equate the force to being the pressure times acceleration. Because remember that pressure is equal to force over an area, excuse me, not pressure, pressure times area. So since pressure is equal to force over area, we can rewrite then that force is equal to pressure times area. So then that moving boundary work, that del moving boundary work, is going to be the pressure times the area times that differential of x. And below you see on the chart that small amount of differential of moving boundary work is based on the differential of volume. So we can, if we integrate this del moving boundary work from state 1 to 2, and we rewrite area times dx to be the, so it's not, instead of the area times the change in the x, the shaft length, the x, we just say the change in the volume, because the volume has changed. It's only changed in the x direction, but it has changed. Then what we get is the integral from state 1 to state 2 of pressure times differential of volume. Well, the integral from 1 to 2 of the differential moving boundary work is all that moving boundary work. So we then say that moving boundary work from state 1 to 2 is equal to the integral from 1 to 2 of pressure times the differential volume. This is equation 1.26, and this is the equation we'll use for a closed system moving boundary work. Now there are some special cases that we'll refer to that make it easier, because this is an integral. It's a little difficult for us to solve right now, so we have some easier cases to solve, some special cases. So let's think first that we have constant pressure. Remember, this is called an isobaric situation. If we have constant pressure, we'll draw our graph. So at state 1, we have a volume 1 and we have a pressure. When we go through the process to get to state 2, we increase the volume, but the pressure doesn't change. Since that's isobaric, it's constant pressure. Well, if we look at the equation, that boundary work is equal to the integral from 1 to 2 of pressure times differential volume. Well, if the pressure doesn't change, it's constant. We can pull it out of the integral. It's not going to change. So we get, now it's pressure times the integral from 1 to 2 of differential volume. Well, the integral of just dv is just v2 minus v1, which you can see by looking to the right of the picture. It just makes this nice rectangle, right? So all we need to know is the area of a rectangle, which is just base times the height. In this case, the base being v2 minus v1, height being pressure. So for a constant pressure isobaric system, the boundary work simplifies down to pressure times that change in the volume. Now another special case we have is constant volume, called isometric, also known as isochoric in Europe and pretty much everywhere else in the world, just isometric here in the US. For a constant volume situation, So now we have pressure starting out at 1. We have volume. We're going to change the pressure, but the volume never changes. So if we look at our equation again, that boundary work is the integral from 1 to 2 of pressure times the change in the volume. Well, if the volume never changes, then we get moving boundary work 1, 2 is equal to 0, which makes sense by looking at the picture, because if the boundary work is equal to the integral, and the integral comes from calculus is the area under a curve, well, in this case, the area underneath our curve is 0. There is no area because the volume never changed. So for a constant volume isometric process, there can be no moving boundary work, which makes sense. It's constant volume. If moving boundary work is we have to move the boundary, and the boundary is defined by the limits of our volume, if we're not changing the volume, then how can we really change the boundary, right? So we've shown it depictively, we've shown it by calculus, and by common sense you would think if there's no boundary change, then we really can't have moving boundary work.